Okay, we're going to talk about error. So last lesson of BC Calculus. Okay, it's typically a lesson, this Lagrange error, that most teachers just skip because they're like, I don't understand it, so I'm not going to teach it. But it's actually not that hard. Okay, so you guys all understand it, obviously, because I'm a good teacher. You guys are good students. All right, good. Using a polynomial to approximate the values of a function, let's say we're using the polynomial at 1 to approximate the function value at 1. The error is your difference between your function value and your polynomial, right? We don't care if we're above or below, actually. We only care about just the relative distance. So we will take the absolute value of the difference between our function value at 1 and our polynomial approximation at 1. Sometimes we like to call that the remainder, R. Sometimes we'll call it E, or error. Okay, doesn't matter. Okay, and we should be familiar with error from a series of constants. Take a typical series where we are adding our terms. You know, we had A1 plus A2 plus A3 plus A4 all the way to AN as n approaches infinity. Some n starts with 1 goes to infinity. We would denote these as our partial sums. This would be P1, which is A1. This is P2, which is equal to A1 plus A2. This would be P3, A1 plus A2 plus A3. This would be P4. And we'd eventually, if this converges to some, S value, this would be our nth partial sum, which would be our sum. And we would see that, hey, our error is right here between any of them. If we looked at our fourth partial sum, we would say S minus P4 is equal to that remainder, R. There's my error. Okay, but of course, if we kept going out, we would see that our partial sums would get closer and closer and closer and closer, infinitely close to my nth partial sum. Okay, but we didn't talk about how we calculated that error until we got to alternating series. And with alternating series, the error was easy to understand and to conceptualize, right? That's because with an alternating series, we had, sums and differences. We started with the value, and then we'd subtract the second value, and then we'd add a third one, and then we'd subtract a fourth one. Et cetera, et cetera, et cetera, et cetera. Add and subtract and add and subtract and add and subtract. And when we looked at the partial sums, we would notice something. And when we started with our first partial sum, which was A1, if it was a positive value, when we subtracted our second one and got P2, that's A1 minus A2, what happened is we jumped over what ended up being our nth sum. Our actual sum of our infinite series. Okay, our sum of here, our ANs here, we said was SN. Okay, when I subtracted A2, boom, I jumped over it. And then I added A3 and I jumped over it. And I got P3. And then when I subtracted A4, boom, I got P4. Right? So we could say, let's say we stopped at P4, and we could say, well, how far away is my sum from my approximation? Well, we could look at it like this. This is my remainder. Okay? Well, we knew that it was bounded by however much we added from our previous term to the next term. We knew that when we added our fifth term, we would go over my actual sum. So our sum is somewhere between. This is how we set kind of bounds for our Sn. I would say Sn was definitely going to be between our fifth partial sum, which was received after we added a term, and our fourth partial sum, which we got from subtracting a term. That made sense, right? Well, we could kind of go beyond that and talk about the bounds of our remainder. And we could say, well, our remainder here, this purple R, let me move some stuff up really quick. This purple R, the max value that it could be, it had to be less than or equal to my previous term plus my next term. Right? Or no, it had to be bounded by what I just added my next term by. Okay? So if we talked about the difference between, in this case, my fourth partial sum and my actual sum, which was my remainder, it had to be less than what I'm adding my next term by. And it could have been the same way for any of these. If I looked at my fifth partial sum, well, maybe I'm subtracting the value. Well, still, I know that when I subtract the value, I'm going to go over my actual sum, okay? And we talked about this with series of constants, so this is just a reminder of that. Now, let's go back to the free response problem we were just doing. And, wasn't it? I think I did it on the next one. No. Now, whatever. Let's go back to the free response problems and see how on these number 6 problems we can find the error bound understanding alternating series. So this was 2012 number 6. I don't know what problem it is in your packet, but you should see it in your packet. And this is part B. It says the Maclaurin series for G evaluated at a half as an alternating series whose terms decrease in absolute value to 0. All this is saying right here is that it converges, right? This is the alternating series convergence test. As the terms decrease to 0, are you alternating, then we converge. Fantastic. The approximation for G of 1/2 using the first two non-zeros of this terms is 17 1/20. They do it for you. Show that this approximation differs from the actual value of G of 1/2 by less than 1/200. Okay, so they are telling you that if this is G and the Maclaurin series for G is this, then approximation for G of 1/2 using the first two non-zero terms would be 1/2 divided by 3 minus 1/2 cubed over 5, and they say that equals 17 over 120. They did that for you. Right? All they want you to do is show that this approximation is different than the actual value of G of 1/2 by less than 1/200. All you have to understand is that this is an alternating series. We start with the first term, 1/6. Then we subtracted a term. Well, I ended up down here somewhere. What am I going to do next? Add a term. I'm going to end up here. Well, we know that the actual sum, which is going to be G of 1/2, the actual value has to be between these two values, right? We know that this is the error and that the maximum error would be this distance that we added. All we need to understand is how much we add to our previous term and show that that term is less than 1 over 200, and we've answered the question. So all we have to know is that g of 1/2 is between, it's definitely going to be greater than 17 over 120, and it's going to be less than 17 over 120 plus 1/2 to the 5th over 7. And I know that the remainder, the approximation, or g of 1/2 minus my Maclaurin approximation using two terms will be less than or equal to the third term that I add. Third term, 1/2 to the 5th times 1/7. 2, 4, 8, 16, 32. What's 32 times 7? 224? Man, look at how they do that. Such a perfect number. This is 1 over 224, which is less than 1 over 200. Check. Larger denominator, less than a smaller denominator. Right? You guys know this, actually. You've done this. You've talked about alternating series error. Cool? So let's do this. This is the concept behind it. Okay? Understand with alternating series, however much you add, that is the bounding error. Okay? But the question should become, what if our series don't alternate? How are we going to understand the maximum error that we can have? Okay? If we go back to series like this, how do we understand, that, oh, well, I know that we have to be within this much. Well, where does that come from? Okay? It's going to come from our friend Lagrange. Lagrange had a theorem. Okay? And it can be proven, and I'm not going to prove it for you. It's a long proof. So the theorem says if we have a finite Taylor polynomial, polynomial means we got finite terms, it's not a series. Used to approximate some function. Okay, and this is how you construct a Taylor polynomial. We're all familiar with this, centered at a value. We'll say centered at C. Well, we know a Taylor polynomial with finite terms will never equal a function. It'll be a good approximation, but we need that infinite amount of terms for us to converge and converge to a specific value. Okay? So Taylor says, well, this P of n will equal f at whatever x value as long as you add a remainder. So, sorry, f of x will equal the polynomial approximation to it, as long as you just add a little bit more, whether you add it or subtract it. This could be above or below the actual value of x, but only if we add an r. Lagrange discovered what the r could be. Lagrange discovered that there must exist a next term with a specific derivative that equals r. And I don't want to say this is C, I'm going to say this is Z. And Z ends up being between where we center this polynomial and where we're trying to approximate. Or it is so C is either between or including X and C. Now maybe C is on the left, X is on the right. Doesn't matter. Okay, let me show you what that means. Okay. All right. Here we go. Let's use Lagrange's theorem. And we're going to use a second degree Taylor polynomial centered at x equals 0 to approximate e of 0.1. Find the guaranteed value of the third derivative of x such that the function plus, so it really should not be that. It should be the third degree Taylor polynomial plus our remainder is equal to e to the 0.1, where the r, and the r guaranteed by Lagrange's theorem, is our third derivative at some z value. Sorry. Actually, no, this is fine. Well, how about we change this to p of 2 plus r, okay? Because r is going to be, if this is the second degree polynomial, this will be that third term with a special derivative, okay? Let me just show you exactly what I'm talking about. So we know that e of x is approximately, and we'll use a second degree Taylor polynomial is centered at 0, so that's the Maclaurin polynomial for e to the x. So 1 plus, f prime of 0 x plus f double prime of 0 x squared over 2 factorial. This is just your Maclaurin polynomial. But we know that with e to the x, it's always, the derivative is always going to be 1. So 1 plus x squared over 2 factorial. Okay? E to the x will be approximately equal to whatever this is with a value plugged in. Of course, e to the x is equal to this with the infinite amount of terms after it. But we don't have an infinite amount of terms, so that's why it's just an approximation. So we know e to the 0.1 will be approximately, and we'll list this as p sub 2 of 0.1, 1 plus 0.1 plus 0.1 squared over 2 factorial. Okay? And we can kind of go and show that approximation and what e to the 0.1 is using a calculator. So we got 1 plus 0.1 plus 0.1 squared over 2 factorial, which is just 2. Okay, 1.105, and that's equal to e to the 0.1, approximation of e to the 0.1. Okay, look at that, pretty good approximation, good to the third decimal place. Well, we want to find the guaranteed value of the third derivative such that this plus that is equal to that. Well, we know that this plus some r will equal e to the 0.1, right? Where r is the next term in a polynomial with a special third derivative. So third derivative at some z value, the z value is going to be somewhere between 0 and 0.1. It's guaranteed by Lagrange's theorem. We will have some z value where the third derivative is equal, third derivative will make this work. So this will be times x to the third power. So again, it would be x minus 0 to the third power but I'll just write that as x to the third power over 3 factorial. And we are approximating 0.1, so actually we should, instead of having x to the third, we'll have 0.1 to the third. Okay? So now there's some derivative times 0.1 to the third over 3 factorial that will be added to this, that will equal that. Now, what is the third derivative of e to the x? Let's just talk about that. So if f of x is e to the x, the third derivative is just e to the x, right? So this is going to be some e to the x value. We'll say it's e to the z. And that z has got to be between 0 and 0.1 as Lagrange guarantees, okay? So let's go ahead and do it. I'm going to just plug this in here, and I'm going to solve the equation using my calculator. I'm going to graph y equals the left side and y equals the right side and kind of go from there, okay? So let's see what we got. So I'll have e to the first, e to the 0.1, and then I have 1 plus 0.1 plus 0.1 squared over 2 plus, and here's my equation, some e to the z, we'll say it's e to the x, times 0.1 cubed over, now 3 factorial is just 3 times 2, which is 6, okay? And x is guaranteed by Lagrange to be between 0 and 0.1. Let's see if we can find that. Okay, kind of tough. I might want to zoom in a little bit. And it might be tough even still to see the intersections of the two. But let's just go ahead and calculate it, see if it can be found. There we go. When x is 0.02, which is between between 0 and 1. So z equals 0.02. Let's just be a little bit more specific. 518852. Okay, and let's just go ahead and make sure that works. I say that e to the 0.1 is equal to this term plus e to the, now it's tough to, we're using e to approximate e, so it's, it's not ideal, but let's just confirm that it is true. All that Lagrange says is that it exists. It's another thing to find it. To the third divided by 6. And I should see the same decimal exactly. And I did. So that's phenomenal. So Lagrange, works. The value that is guaranteed was found. That guaranteed value is, the next term with a special derivative. It's not a derivative at 0. It is instead a derivative between where we're centering and what we're trying to approximate. Okay, some derivative between what we center and what we approximate is what we're trying to find, or what is guaranteed to exist. Okay, so it exists, and it's just from a next logical term in a polynomial, Taylor polynomial. What ends up happening is like, okay, this exists, and it's some value, I guarantee you, it's some value between x and c. Well, what if we wanted to know, well, let's say we stop here, and this is where we stop. How far off are we at maximum? What is a bounded error? Just like with our alternating series, when we end up with the previous term, we add our next term. We know we're going to go over, but at least we know that we are between those two values, right? Okay, well, if you think about it, if we know this value exists, and it does exist, even though I didn't show you it exists. If we know that what the maximum value this could be, because this isn't going to change and this is going to change, well, then we know what our error is going to be bounded by. And Lagrange's kind of theorem, which just says this R is some next value that exists, well, now we know kind of like what the error is going to be bounded by. This is kind of the basis of the lesson, the Lagrange error bound. We know Taylor's theorem, Lagrange's theorem to be true. We could see the maximum amount we are off by if we know what this is. This is Lagrange's error bound. Since you take a Taylor polynomial, and Lagrange says you can add the next term with a specific next derivative, and you will get the exact value. Well, if you are able to maximize this next term's derivative, well, that means you know the maximum amount that you can add to your Taylor polynomial, and that will give you the maximum amount you could be off by. It's a simple concept if you understand Lagrange's theorem, where you take a Taylor polynomial, all you can do is just add the next term with a specific derivative. I didn't show you what the derivative was. I wanted to show you an example that exists. And if we know what the maximum value of that derivative could be, we know what its error is bounded by. Does that make sense? I'll walk you through it one more time after you copy it down. And maybe not use A, we use C sometimes, use A other times. I like using C, centered at C. And typically the maximum value, this M, is at either X or C. It's typically at an endpoint. Okay, let me walk you through it one more time. We know we have a Taylor polynomial. It's going to be an approximation. P of n is going to approximate f of x. Well, f of x will equal P of n plus a remainder. Lagrange discovered that take the next term at a specific derivative at some value between x and the value that you're trying to approximate, and that will be the remainder. Fascinating. We can just look at the next term with a specific value here. And that value is between this x value and the c value. Oh, wait. No, never mind. Okay, cool. Well, then, that means if we know that, we could just maximize this next term's value, and that would be the maximum amount that we could add or subtract to it. That would be the error bounded. We know we are off by as much as that much. Okay? So let's do a couple problems, and I'll show you that it's no big a deal. Like 2011 number 6, probably part D. Okay, we have the graph of the fifth derivative of x. We are asked to let the fourth degree Taylor polynomial for f about x equals 0 be p sub 4. Use the information from the graph of the fifth derivative and its absolute value to show that p4 of 1/4 minus f of 1/4 is less than 1 over 3,000. Okay? Well, I know that p4 of 1/4 plus some remainder would equal f of 1/4. And I know that that remainder is some fifth derivative of my value at some value times x minus 0 is my center to the fifth over 5 factorial, right? Well, the maximum that the remainder could be is the maximum value of this fifth derivative at some value times x to the fifth over 5 factorial. Well, I'm trying to approximate p of f of 1/4. So we are centered at 0. 0 is the c value. This 1/4 would be the x value. So I put 1/4 in for the x. Put 1/4 in for the x. All I need now is m, the maximum value that our fifth derivative can take between 0 and 1/4. Let's look at our graph. What would be the m value that I would choose for the fifth derivative? Between 0 and, I guess, 1, 2, 3/4 and 1/4. What is the maximum value of this fifth derivative? Looks like it's this value right here, right? That looks to be about 30. Now, if you look in the key, they just chose 40, and 40 worked as well. But I would probably choose 30. And all you have to show is that this remainder, which is as much as 30 times 1/4 to the fifth over 5 factorial, is less than 1 over 3,000. And if you had a calculator, it's easy to show that. If you don't have a calculator, you can show that just by leaving it like this and assuming that it's true. Okay, I'm going to do a couple more examples, and you'll have your quiz key online to help you with these problems. You'll have a couple of these problems on your test for Thursday if I see you Thursday. Okay? If you're here Thursday, let's be here Thursday. If everybody's coming to school Thursday, I expect you here Thursday. We'll take the test. If nobody's coming to school on Thursday, I'll talk to you juniors who are here, and we'll discuss whether we want to practice more or just do it when everybody else is here. The test isn't going to go away. Here comes a couple more examples. And I'm going to go back to that other problem, figure out why it didn't work. All right, 2008, number 3. Here are derivatives of h. The 4 derivatives are increasing on the interval from 1 to 3. Okay, so from 1 to 3, all of my derivatives increase. Okay, so these are increasing, these are increasing, these are increasing. Use Lagrange error bound to show that the third degree Taylor polynomial for h about x equals 2 approximates h of 1.9 with error less than 3 times 10 to the negative 4. All right, well, I know that my third degree Taylor polynomial for h about 2. So if I use it to approximate 1.9, I add a remainder, it's going to equal f of 1.9, or sorry, h of 1.9. And I know that remainder is going to be some fourth derivative, the next term. So h to the fourth prime of some value times x minus c to the fourth all over 4 factorial, right? So it's my next term with some special derivative. Well, here this c, we're centered about 2, so our center for this Taylor polynomial is at 2. Okay, and I'm going to approximate 1.9. So my remainder is going to be 1.9 minus 2 to the fourth. Over 4 factorial. Okay, well, what is our error bound? Well, I know that the remainder has to be less than the max value that this fourth derivative can take on my interval from 1.9 to 2. Okay? So times 0.1 to the fourth, it's negative 0.1 to the fourth, but that's fine, times 4 factorial. And let's look at this. So I don't have 1.9, but I'm told that these four derivatives are increasing on the interval. So I believe they're increasing in every direction. This way, oh, okay, this way we're increasing, this way we're increasing, we're not increasing this way, obviously. So let's see, 448 over 3 is 149. So we're increasing here, we're increasing here. Well, this is the fourth derivative, so we need to be increasing 18 to 584 over 9. And since we are increasing, that means the derivative at 1.9 is going to be less than the derivative at 2, and the derivative at 2 is going to be the max derivative that I can take. Most likely this value, this r, is not going to be this, but the max derivative it could take would bound my r's value. So I can actually just say my r has to be less than 584 over 9 times 0.1 to the fourth over 4 factorial, and I'm going to assume that's less than 3 times 10 to the negative fourth. And for this calculator, you actually have, for this question, you actually have the calculator to use. So I'm going to do the math really quickly. So 584 divided by 9, oops, times 0.1 to the fourth, divided by 4 factorial, gives us that. And I compare that to 3 times 10 to the negative fourth, and I can see, obviously, that 2.7, my remainder r, is less than 2.7037 times 10 to the negative fourth. Okay, so boom, let's do another one. Let f be the function given by f of x equals sine of 5x plus pi over 4. Let p be the third degree Taylor polynomial for f about x. Find p of x, and use Lagrange error bound to show that f of 1/10 minus p of 1/10 is less than 1/100. And this is r, of course. Okay, so p of x, third degree Taylor polynomial for f about x equals 0. Okay, so first, p of x, f of 0, we're centered at 0, plus f prime of 0, x minus 0, over 1 factorial, plus f double prime, we need a third degree of 0, x minus 0 squared, over 2 factorial, plus our third degree, third derivative, x cubed over 3 factorial. Okay, f of 0, if I plug in 0, I got sine of pi over 4. That's root 2 over 2. Okay, this is interesting. If I take my derivative, I get cosine of 5x plus pi over 4. So times 5, that's f prime. If I do f prime of 0, it's the cosine of pi over 4, which is root 2 over 2 times 0.5. So it's root 2 over 4. Root 2 over 2 times 5 times x. Second derivative, I go to negative sine of 5x plus pi over 4 times 25. Sine of, plug in 0, and I get the negative sine of pi over 4. So that's negative root 2 over 2 times 25. So negative root 2 over 2 times 25 x squared over 2 factorial. Okay? Third derivative, fun. This would be negative cosine 5x plus pi over 4 times 125. At 0, negative cosine is also negative root 2 over 2. So we get root 2 over 2, 125 x cubed over 3 factorial. Okay, so that's p sub 4 of x. They asked you to find p of x, so I'd probably have to find the nth term. It looks like they will go positive, positive, negative, negative, positive, positive, negative, negative. So to do that, the alternating, I probably would switch it into 2 different ones. Let's not worry about that. Let's just stop at the 4th derivative. And let's go here. Use Lagrange error bound to show that f of 1/10 minus p of 1/10 is less than 1 in 100. So I use the third. Oh, p of x is the 3rd degree Taylor polynomial. So this is p of x. And I don't know why it said this is p of x. This is the third degree Taylor polynomial. Okay. Well, I know that my 3rd degree Taylor polynomial went at 1/10 when I plug in 1/10 everywhere. And I add a remainder. I'm going to get f of 1/10, which is sine of 1/2 plus pi over 4. Okay? Well, that remainder, by Lagrange's theorem, has to equal some next derivative. So we only have the 3rd. So the 4th derivative of some value, it's the 4th derivative of some value, and that value is between x and c, or included, times the x minus c. So I'm using, the 1/10 minus 0, so 1/10, to the 4th power, it's my next term, all over 4 factorial. And now I know that that remainder has to be less than or equal to the max value that derivative can have to the 4th power over 4 factorial. Now here's your key. What is the max value that we can have? Between 0 and 1/10. Well, I got to figure out what the 4th derivative is. So the 4th derivative ends up being positive sine, so I go back to the regular one, positive sine 5x plus pi over 4 times 125 times 5 is 625, I believe. 10, 11, 12. 625. Okay, so that's the 4th derivative. Now, I got to think about sine's maximum value and minimum value between 0 and 1/10. I know that the maximum value of sine is usually 1. It's the maximum value at 1. Maximum value when it's equal to 1. But my values are going to be constrained to between 0 and 1/10. Now, I think about this, and let me just make sure I got the right thing, 0 and 1/10. Yeah. I think about it, the sine of, pi over 4 is root 2 over 2. Okay, now what if I do the sine of pi over 4 plus, if I plug in 1/10, I got a half. Now, what's a half? And what's pi over 4 plus a half? Is it bigger or larger than what would give me pi over 2? Sine of pi over 2 would be the max completely, right? Well, pi over 4 is 3.14 over 4, right? So this is greater than a half. So that means when I'm adding a half, I'm not going to be at the maximum value. However, I am going to be increasing in my values. So this actually will be the max value that I can have between 0 and a half. It's the sine of pi over 4 plus a half times 625. Now, you don't know what this value is, but that is what you should have here. But I guarantee you that since you know that the absolute maximum that you could have for sine is 1, that they're going to want you to put 625 here. But I'll show you how either way it'll work. So r has to be less than, sine of pi over 4 plus 1/2 times 1/10 to the 4th over 4 factorial. and this should be less than 1 over 100. Let's just do the math. I'll show you that if I used even a larger value than that, if I had a maximum value of 625, 625 should be here. Times 1/10 to the 4th divided by 4 factorial. That's less than 1 over 100. Yep. Now, if you don't have a calculator, you're just going to go ahead and assume this is correct, and it is. 0.002. You're going to just assume this is less than 100, and you're going to be fine. If I use 625 instead of sine of pi over 4 plus a half, I get 625, 1/10 to the 4th, divided by 4 factorial. And I got the very similar value, 0.0026, okay, which is definitely less than 1 in 100. Okay, let's do another one. So, 2004b, let f be a function having derivatives on all orders for all real numbers. The third degree Taylor polynomial for f about x equals 2 is given by this. Use t of x to find an approximation for f of 0. Is there enough information given to determine if... Okay, this is a good one to talk about with the relative maxes and mins. So approximation for f of 0 will just be our value of t of 0. Now, this is a third degree Taylor polynomial about x equals 2, so it's not going to be great. It's not close to 2, but whatever. We'll have 7 minus 9 times negative 2 squared minus 3 times negative 2 cubed. Okay, that'd be my approximation. So enough information to given to determine if f has a critical point at 0. Well, if f has a critical point at 0, f prime at 0 should equal 0. Okay, well, if f prime at 0 equals 0, then we should see that we would assume that the Taylor polynomial would have a 0 as well, but we don't know what exactly f of 0 is. This is just an approximation. So unless I was given what f is above, I don't know. So I'm just going to stop there, and this is my approximation. We're told that the fourth derivative of f satisfies the inequality fourth derivative of f is less than or equal to 6 for all x's in the closed interval from 0 to 2. This is very important. Notice how they gave the closed interval from 0 to 2. They're talking about the max value that the fourth derivative can take on just your interval. That's why I'm talking about, pi over 4 plus a half instead of going straight to pi over 2, because we're not adding enough to get to pi over 2 on that previous problem. Yeah. Anyways, use Lagrange error bound to approximate error bound on the approximation of f of 0, part C, to explain why f of 0 is negative. Okay, cool. So t of 0 plus some remainder is equal to f of 0. T of 0 is this. I'm probably going to have to actually find this. Let me do it really quick using a calculator. It's annoying that they have you do that, but I got negative 5. Okay, so negative 5 plus remainder is equal to f. Lagrange says that the remainder has to be some next term in our Taylor polynomial. So that'd be my fourth derivative at some value. This value has to be between x and c, or included x and c, times my, x minus my c to the 4th power over 4 factorial, right? Has to be that. Well, x in this case was 0 and c was 2. My polynomial was centered at 2 and I'm approximating 0. So I get negative 2 to the 4th over 4 factorial. Well, I know r has to be less than or equal to the max value that can obtain times negative 2 to the 4th over 4 factorial. What is the maximum value that we can obtain? We are told that the maximum value of my derivative has to be between 0 and 2 is at max 6. Told to us in the problem. So 6 is negative 2 to the 4th over 4 factorial. Negative 2 to the 4th is 2, 4, 8, 16. So 6 times 16 over 4 factorial. Okay, now this is important. Now I actually have to do that. And I actually get 4, which is phenomenal. Okay, 4. Now, the question is, use the Lagrange error bound to explain why f of 0 is negative. Well, t of 0 was negative 5. Plus, my remainder is equal to f of 0, right? Well, the max value is 4. So if I add my maximum value that we're adding by, we get to negative 1, which is the max value that f of 0 could be. Since that's the max value it could be, we know that f of 0 must be negative. Okay? That's Lagrange error bound. It's actually not that difficult, and I'm sorry that my example didn't show you that this value existed, because it does. This r is actually, it's a fascinating thing, a next term with a next derivative at some value between our two values that we're either approximating or centering our polynomial by. Okay? I'm going to go back and check that. Thank you.